Hello everyone, my name is Maggie Tansky and today I will be walking you through my report for Lab 1, Constant Velocity. In this experiment, we will analyze a real-life example of constant velocity. However, in the case of any model that we ourselves are able to construct at home, we are not sure whether or not the object's velocity is actually constant because we do not know the sum of the net forces acting on the object. In this experiment, we will use Newton's first and second laws of motion to help us determine whether or not an object has a constant velocity. Newton's first law states that every body persists in its state of rest or of moving with constant speed in a constant direction, except to the extent that it is compelled to change that state by forces acting on it. With this information, we can infer that in order for an object to have a constant velocity, the sum of the net forces acting on that object must be zero. With this in mind, we go to Newton's second law, and we can show that when F net equals 0, V initial and V final must be equal. Therefore, the object's velocity is constant. We will use this concept later to create a computational model of constant velocity. For this experiment, I decided the system to be a softball, and the surroundings to be the floor it rolls across as well as everything else in the universe. Within Tracker, I designated the origin so that the ball's movement would be in the positive x direction. Now I will run the program, and this is what we get. As you can see, the position versus time graph in the upper right-hand corner is linear, which bodes well for the possibility of the ball having constant velocity. Now we will take a look at the table in the lower right-hand corner, which gives us the time, x position, and y position, which we will not be using, of the ball at each 0.033 second interval in the video. The values for the x position are in centimeters, so we need to change the values to m for the next step, where we will take note of the initial and final values for the time and position and use them to determine the initial velocity of the ball. The initial time was 0 seconds and the final time was 0.934 seconds. The initial position of the ball was a vector with 0.00157 meters in the x position, and the final position was a vector with 0.7196 meters in the x position. Note that we have changed the position from centimeters to meters, and we have written them as vectors. We will use the formula for velocity to determine that the initial velocity of the ball is a vector with 0.768 meters per second in the x position. We will now use the sample glow script code to create our computational model. I made sure that the code matched the system I had set up, so I changed the radius of the ball to be 0.04826 meters and the mass of the ball to be 0.1985 kilograms so that the model would describe an actual softball. Next, using the data gathered from Tracker, I changed the initial position to be a vector with 0.00157 meters in the x position and the initial velocity of the ball to be 0.768 meters per second in the x position. I also made sure that the time step was correct, or delta t, to be 0.033 seconds. For the calculation, we will use Newton's second law, as mentioned earlier, to create an iterative loop that predicts the new position and the new velocity over a series of time steps. We will tell the code to find the new velocity and the new position every 0.033 seconds until the clock reaches 0.934 seconds, which is the final time found in Tracker. We will also tell the code that for every moment inside the loop, the net force is 0. Next, we will use Newton's second law, and knowing that if F net is 0, Vf will be equal to Vi. Now, the code will predict the next velocity value using this. And then afterwards, we will also tell the code to predict the next position value using this formula. Finally, we will tell the clock to advance to the next time step, here. Outside of the while loop at the bottom of the code, we will uncomment line 71, which will give us the time and position output for each step once we run the code. And now, running the program, we see this. As you can see, the ball is moving in the positive x direction in the same manner as the original video, and the position versus time graph looks very similar to the other graph we saw in Tracker. The time and position data is also given, which we will use in a moment. By controlling the conditions of the computational model, we are able to create and see a perfect example of constant velocity. We can use this data from a perfect constant velocity and compare it to the data from Tracker and see whether or not the original softball is anywhere near to constant velocity. On the left-hand side, I have arranged the time and position values given by Tracker. On the right-hand side, I have arranged the time and position values given by the computational model. In the center, I have used the values to plot a position versus time graph, with the blue line representing the observed motion from Tracker and the orange line representing the predicted motion from the computational model. As you can see, the two lines are very similar and even overlap closer to the end. We can conclude from this that the velocity of the softball is very near to constant, which also means that the sum of the net forces acting on the softball is very near zero. To finish up this report, I will be answering two questions. What if, and what does it mean? What if I had changed the orientation of the axes in Tracker? How would my results change? So if my video wasn't upside down, the ball would be moving towards the negative x direction. This would cause the results to change in that the position versus time graph would go from the top left-hand side to the bottom right-hand side because the object's position value at each time step would be increasing in the negative direction. Next, is it possible to say how many pushes and pulls are added together to give a zero net force? I have drawn a free body diagram to the best of my ability of the softball, and to my knowledge there are at least 4 forces acting on the ball so that the net force equals 0. I think these are normal force of gravity, friction force, and the pushing force of me pushing it across the floor.